Reactive machines, the foundation of AI. Artificial intelligence is a vast field, encompassing many different approaches to creating intelligent machines. One of the most fundamental types of AI is reactive machines. These systems operate on a simple principle: react to the current situation based on pre-programmed rules. Reactive machines don't possess memory or the ability to learn from past experiences. Their actions are solely determined by the immediate input they receive. This makes them efficient for specific tasks but limits their overall adaptability. The core of a reactive machine lies in its set of predefined rules. These rules dictate how the machine should respond to various stimuli. When the machine encounters a specific situation, it searches its rule base for a matching rule. Once a matching rule is found, the machine executes the corresponding action. This process happens in real time, allowing the machine to react quickly to changing circumstances. The simplicity of this approach makes reactive machines very reliable. Reactive machines are characterized by their lack of memory. They don't store past experiences or use them to inform future decisions. Each decision is made independently, based only on the current input. Another key characteristic is their deterministic behavior. Given the same input, a reactive machine will always produce the same output. This predictability is valuable in applications where consistency is crucial. One of the main advantages of reactive machines is their speed. Because they don't need to process past data, they can react almost instantaneously. This makes them suitable for time-sensitive applications. Another advantage is their simplicity. Reactive machines are relatively easy to design and implement. This makes them a cost-effective solution for certain tasks. The lack of memory is also a significant limitation. Reactive machines cannot learn from their mistakes or adapt to new situations that weren't explicitly programmed. This limits their versatility. Another disadvantage is their inability to handle complex or ambiguous situations. Because they rely on predefined rules, they may struggle when faced with unexpected input. They are only as good as the rules they are given. A famous example of a reactive machine is IBM's Deep Blue, the chess-playing computer that defeated Garry Kasparov in 1997. Deep Blue didn't learn chess in the way a human does. It relied on a vast database of chess games and a powerful evaluation function. The computer analyzed millions of possible moves and chose the one that maximized its chances of winning. It was a brute force approach, but it proved to be highly effective. Deep Blue's success demonstrated the potential of reactive AI in complex tasks. Deep Blue's architecture was specifically designed for playing chess. It consisted of specialized hardware and software optimized for move generation and evaluation. The system could analyze up to 200 million chess positions per second. The evaluation function assigned a numerical score to each position, reflecting its favorability for Deep Blue. This score was based on factors such as piece count, pawn structure, and king safety. The computer then selected the move that led to the highest scoring position. Despite its impressive performance, Deep Blue had limitations. It lacked the intuition and creativity of a human chess player. It couldn't learn from its mistakes or adapt its strategy in response to unexpected moves. Deep Blue's success was largely due to its superior processing power and vast database of chess knowledge. It was a triumph of engineering, but it wasn't a true demonstration of general intelligence. It was designed to do one thing, and do it very well. Reactive machines are used in a variety of other applications. They are commonly found in simple control systems, such as thermostats and washing machines. These devices react to changes in temperature or water level based on pre-programmed rules. They are also used in robotics, particularly in tasks that require precise and repetitive movements. For example, assembly line robots often use reactive control to perform their tasks. These robots follow a set of instructions to complete each step of the assembly process. Reactive AI is also prevalent in video games. Non-player characters, NPCs, often use reactive rules to respond to the player's actions. For example, an enemy character might attack when the player gets too close. These reactive behaviors can create a more immersive and challenging gaming experience. While not as sophisticated as more advanced AI techniques, reactive AI is still a valuable tool for game developers. It provides a simple and efficient way to create believable and engaging characters. While reactive machines may seem simple compared to more advanced AI systems, they still have a role to play in the future. They are well suited for tasks that require speed, reliability, and predictability. As technology advances, reactive machines may become even more sophisticated. They could be combined with other AI techniques to create hybrid systems that offer the best of both worlds. For example, a reactive machine could be used to handle routine tasks, while a more advanced AI system could be used to handle complex or unexpected situations. Reactive machines represent a fundamental building block in the field of artificial intelligence. While they lack the learning capabilities of more advanced AI systems, they offer speed, simplicity, and reliability. They are used in a wide range of applications, from chess-playing computers to simple control systems. Understanding the principles of reactive machines is essential for anyone interested in AI. They provide a foundation for understanding more complex AI techniques. As AI continues to evolve, reactive machines will likely remain an important part of the landscape. Thanks for watching Tadhem.